And welcome to you all to this webinar where I am going to address some of the possibilities that can be applied on using agent-based modeling using ABM Lab in Mike software. So that's what we're going to touch base on. And yeah, this is an image where we're going to. So, well, how does this fit in with agent-based modeling? But essentially, most of you probably have, some of you might have seen agent-based models in action before. And as you can see, what you see from the picture here is one of the more famous cases where agent-based models have been used. This is from Lord of the Rings, where they used agent-based models to have the major armies clash together. So instead of having to animate each small little individual and animate the behavior of each little small individual, they created an agent-based model where they tried to define overall behaviors for each individual and then actually let the individual kind of decide by themselves how they should interact with other individuals on the field. So that's a very good example of how an agent-based model has been applied in real life, and where most people would actually recognize it, maybe without knowing that it was actually agent-based models. So the aim of this webinar is to talk about agent-based models in Mike and give you a little bit of an overview of what it is in a Mike context, but also more generally. And this means that we're going to talk a little bit about the possibilities of using agent-based models. What are the options? What can they be used for? We're going to look into a little bit of the mechanistic side of agent-based models, both within the Mike realm, but also generally how do some of them work on a more principle level. And then we're going to look at some examples, and so we're going to see how you can visualize agent-based models, and also we can talk a little bit about how to analyze this, but that's more of a thing for the upcoming course later this year. And yeah, to short, my name is Lars Mortensen. I'm a spatial ecologist with the DHI. I've been working with ecological modeling and ecological models for the last 10 to 12 years, and more agent-based models more specific within the last 2 or 3 years. So I have a very broad knowledge base on how to approach ecological modeling, and also within how to apply this within an agent-based model field. But to step a step backwards, what is a model? And it's a phrase that we use a lot in everyday life, but also especially within science. And to put it simple, a model is a simplification of real life. So real life tends to be too complex to embrace either mathematical or conceptual. So we use models to describe real life, often in a very simplified version. As it was be seen here. A good example of this is an old example. This is the amount of furs traded of snow leopards, snowshoe hares, and the Canadian lynx over a series of years, and it's used as a proxy for the population size of each individual of each species. And as you can see, they kind of fluctuate together, but not completely together, and it's a little bit off, but they do fluctuate together. And a model of that can be this, and that is what is called a Lotka-Voltaire predator-prey model. So this is a simplified version of the snow hare Canadian lynx interaction, simplified in a mathematical equation, and then displayed like this with more rhythmic patterns. But it illustrates nicely how the two things synchronize together. This is also called what is called a top-down population model. One of the things with top-down population models are that they view the populations from above, and they don't make distinctions between individuals within the populations. They assume that all the individuals are the same. They have the same characteristics. They have the same growth rate, the same birth rate, mortality rate, digestion rate, bioenergetic rates. They're all the same for each individual. However, that's not usually how real life works. Real life are simply usually more complex and usually have at least the odd one out within a species. But generally, species are within a species. There'll be a large variety of individuals within the species. There'll be big ones, small ones, thin ones, fast ones, quick ones, clever ones, stupid ones, and so on. So how to embrace this in numerical modeling and population models? How to distinguish these rather complex issues that arise when you want to look at how individual beings affect, how the individuality of beings within a species actually affect the overall population change. This is an issue that's too complex for normal top-down population models. They have a hard time embracing this, especially mathematical. So agent-based model comes in. An agent-based model, also called an individual-based model, and it also have a lot of other names. It's essentially a model that describes the autonomic behavior of states and states of agents, objects, or individuals. So what does this actually mean? It means that instead of a population model and a top-down population model that describes the overall behavior of a population in terms of growth rates and stuff and the likes, an agent-based model describes the behavior of an individual and the state of an individual or an agent or an object it can be. And then the sum of these behaviors will make out for the population effect or consequence or change. That means that each individual will have its own type of behavior, typically, of course, specified within a range, because, I mean, it would be a hard time saying and sitting and programming each individual. So it'll be over ranges, but it'll still be individual. That means that agent-based, what we can model with agent-based models and within ABM Lab of Mike is rather diverse. It can be anything from vessel traffic to whale migration to fish flocking and other properties. Generally, anything that involves an individual or anything where you can specify things as an object. This can also be a blob of oil in the sea. As long as it's not dissolved in the sea, the blob of oil can be defined as an agent in its own and be given properties to behave according from that. And then that means that within the Mike framework developed here at DHI, we have a tool called Ecolab or ABM Lab, which is embedded within the Ecolab tool, and then which is then embedded in the Mike software. So it's something within something within something. But the benefit of this ladder where everything is embedded into each other is that it's also very well integrated within each other. That means that the agent-based models that developed within the Mike software have an ease of reading off the Mike hydrodynamic models, for instance. It also can read off our habitat models or off of our noise models. And that means that it's a nice integration between all these. That means that you can read off things that you want your agents to know when behaving in your simulations. That means that agent-based modeling, when using the ABM Lab, Ecolab in Mike, it means that on a completely overall basis, it allows for this spatiotemporal representation of hydrology, and it allows the agents to read off this representation. That means that you can model multiple levels, and you can also model the Illyrian framework into the agent-based models. The ABM Lab also have this. It is a particle tracking algorithm. It is set up so that you track how particles move in your simulated domain, but each particle gets to decide what to do on its own. They are not obliged by the other particles. This is what differs it from standard particle tracking modules, and it also allows us for doing a lot of other things. So what does it look like? What does an agent-based model look like in detail, specifically within ABM Lab, but this also accounts for ABM models in general? It is that it involves a range of properties. First and foremost, in an agent-based model that's spatially specific is that you get an XYZ coordinate at each time in your time step in your model. Of course, if you don't have a spatially explicit agent-based model, there's no geography in it. It also involves movement. There's the specification of movement in direction and speed. That's what the agent gets to decide. It involves a lot of states, internal states of the agent. What's the volume of the agent? What's the mass of the agent? How old is the agent? And so on and so forth. And then you specify some rules. What happens if you don't get food? Do you die? What happens if you encounter other of your same species or the opposite sex of the species? Does that involve in mating and subsequent offspring? And all these rules, they're set up within your framework, and that's what enables the agent to decide what to do in life. But so, as an example, here's a very small example of a dummy agent. It's not a specific species or vessel, or it's not anything from real life. It's just set up to illustrate how a simplified agent-based model can work. Over to the right is a model domain where we can see it's a very conceptual river basin where the water will flow through, and there's a patch of, it can be chlorophyll, it can be something, a resource that the agent will go looking for. These agents they've just been told to move by currents. So move by currents, but when they encounter a food resource, they'll stop, assimilate it, and then they will move on when the resource is done. So you can see the agents are released. They've moved by the currents, indicated by the arrows. When seeing the food source, they'll deplete it, and then they'll move on according to the currents. And the specified thing about this is that each dot on the screen here was acting independent of the other dots, and they were making their own decisions based on the currents and the food resource available for them at the time. And this is created by the way we define movements. And this is, of course, mainly for ecological movement and mainly for animal species. But you can also apply it for other situations if it becomes necessary. But then you will have, maybe sometimes you will do direction and speed in other forms. Within ecological modeling, we don't usually either use something called the correlated random walk, which is a way of dictating walk that in each time step, the heading of the walk will be random. It'll choose between a random number, a random direction number. However, it's just, oh, yeah. However, it will mainly choose a direction according to its own nose. So it will be correlated according to where you came from. This is a way most animals will move in real life. Then it will choose a random direction, but depending on how much it wants to move forward, the randomness becomes less according to where it came from. This can be accelerated into a kinesis walk, where it'll alter between two different movement states. It'll either be, if it's in a bad place, a place it doesn't want to be, it can move in one fashion, where it maybe will move more sporadic to find more optimal habitats. But then when it enters a place that it wants to be, a high quality habitat, food patch, um, adequate temperature and like, it'll change movement behavior into something else. This is what's called a kinesis walk. And then lastly, and this is applied, of course, for all animals, but this can also be for vessel traffic and other things where you have a restricted search function. That means that the agent will assimilate information on the surrounding area, and then it will choose the direction based on the information that it receives. It means that it'll head towards where it's been specified to go, or where it will be optimal according to where it prefers. It can be towards deeper waters. It can be towards the available harbor space in the harbor, and so on and so forth. And this is expressed like this. This is another agent-based model where the agents move according to this kinesis walk. When it's out in the blue area, it will move rather straight because that's suboptimal habitat. And when it then encounters better suited habitats, such as the red or the yellow areas, it will change behavior and move a little bit more squared. And you can see this is why they actually aggregate in these patches, not completely, but more than it does in the blue areas. If this is completely random, they should be scattered all over the place. In this, there's an example of a static habitat map. As you can see, that the habitat map behind the agents, it's static. It doesn't move or change in time. Here in DHI, we prefer to use something called dynamic habitat modeling, where we get the habitat quality change in time. This looks like this. This is an example from the northern coast of Norway, where you can see the habitat quality changes with time. It becomes better at points in time, and then it lessens other times. This is also what reality looks like to a large extent. And the habitat qualities and habitat patches changes in time, and some are more suitable in some times, and then changes and other things will be preferable in another time. Another example of movement is the classical predator-prey movement. So here again, generic predators, the square ones, and prey, the round ones, and how they navigate throughout space. In this ones, the square, the predators will try to navigate towards a prey if it finds one. This is using restricted search function. It won't walk in a straight line. It'll still use a correlated random walk, but it'll be correlated towards a prey. And then when it finds a prey and encounters a prey, it'll assimilate it. And then if there's nothing near it, it'll turn yellow and then change its foraging behavior, and it'll be more random where it goes around until it finds a prey, and it'll start going for that again. So this is an example of a classical predator-prey setup model. It should, of course, be suited for whatever predator-prey you wanna model. Adding some simplistic behavior patterns also induces some very interesting emergent properties, such as this, where we are modeling social behavior. So in this, we also made a very simple model. They will walk according to a correlated random walk. However, we assigned rank to each agent, ranking from 1 to 4. If you're a 4, then you're a dominant individual, meaning that you'll walk where you want to go. But if you are a 3, then you'll follow a number 4. And if you're a number 1, you'll follow a number 2, a number 3, and number 4, and so on. And this results in these flocking behaviors, where you can actually see, by just adding such a simple thing as just making this hierarchy, you can actually make them generate very nice flocks when they travel around. However, they can also split up the flocks actually because of this random walk, and when usually the flocks becomes too big, they'll become destabilized and actually at sometimes split up and form some new flocks depending on the hierarchy within the in the other flocks. But this is a very nice way of demonstrating flocking behavior within, for instance, the bird species or other species that's retain hierarchies. So under the hood, how does it actually look like when you have an agent-based model in Mike Ecolab? And it doesn't look as fancy as the videos. It looks like this. So, oh, like this. See if I can. I need to see if I can. Oh, I can't do that. So it's made up of an Ecolab overlay. That means that the top part of the screen, in the top part of the small screen, you can see an Ecolab setup, but then you can also see a particle class setup. And each particle class is made of some state variables, some constants, restricted search function, and then the arithmetic expressions. The arithmetic expressions are the ones that are governing the behavior of the individuals. This is where you put all the behavior rules, where the other ones are more either constants, meaning that constants that needs to be read, or state variables, which are variables that change in time. That could be anything from body mass to height to age and other variables that you need to change, that needs to be changed in time for the individual. And lastly, you have the horizontal and the downward movements of the agents. These ones are the ones that express the movement of the individuals. So the result of the arithmetic expressions and everything that comes before it results in the horizontal movement in terms of speed and direction. And again, if it's a spatially explicit model. Agent-based models does not need to be spatially explicit. And then, of course, you just have things that stand still. So one of the possibilities of using agent-based models around, there's some different ones. One of the classic examples are the noise impact assessment on, for instance, marine mammals when conducting either seismic surveys or offshore wind farm construction. And here we have a hypothetical marine mammal. It's not a specific species, but it's a hypothetical marine mammal that's migrating along a coast. They're migrating according to a directed correlated random walk, so they'll try to make their way west, sorry. But during the migration, at some point in time, there will be a noise impact like this, and they'll try to escape the noise. So they have a behavior rules and saying that if noise level exceeds something, they'll have to try to avoid it. And by implementing this and the behavior rule, you can easily see how the displacement of the agents occur. But using this, you can also calculate how, if you include avoidance behavior into your models, how much of the sound reduction do you get for each individual. So if you don't stay in an area, but you leave, you then reduce the amount of sound you receive on an overall period. And these are the tools that you can use agent-based models for instance, within noise mitigation and noise assessment. This is also seen in this one here, where you have this is a fish that's swimming around, having fun, and then you have a seismic survey going back and forth. And each time the seismic survey ship comes within a certain distance of the agents, they will react due to the sound emission, and then they'll return when the ship stops. Using this, you can see that it actually, due to the drifting of the particles, they have a slight north and south movement. It creates a displacement field just on the right side of the survey vessel. This is something that would be very hard to model if you were just modeling using top-down population models, because you don't get this geographic explicit change in time. And this is actually very nice to see. Another thing is connectivity studies, dispersal studies, things where you want to know something about how things disperse in time and place. This example of a larval dispersal, where you can see that the larvae are being emitted in one place, but then they flow according to the prevailing currents and structures of the geography. And then you can see how it actually generates the connectivity patterns that can be used to assess hotspots for larval deposits and the likes. And it also looks just very nice with the colors. Lastly, something else. Most of the things have been uh, mammal or animal at least models. But this is a good example where you can also use vessel traffic. So this is shipping vessels that's been modeled in an agent-based model uh, with their but with very simple movement patterns that they have to go along certain transit certain lines. They of course don't move in correlated random walks because that would be a little weird for a ship to sail like that. But of course, this in this model we don't use hydrodynamics, but hydrodynamic variables could be included in this, so you would get drift of, for instance, the drift of the vessels and how they had to compensate according to prevalent hydrodynamics. This could also be used to assess the collision risk with marine mammals if you included an agent-based model for marine mammals that would swim into this area, and then you can actually assess the likelihood of having marine mammal collision risks in the area. So in summary, the agent-based models, it's models that enables you to model relatively complex systems by embracing individuality within the systems rather than assuming everything is the same within the system. It allows for the modeling of multiple objects, individuals, ranging anything from a boat to a whale and to a fish. And especially within the Ecolab framework, there is this heightened connectivity between both the agent-based model and the physical world, which makes it a very strong tool to do these models within the system because it's already tight knit together.